Okay, we're going to design a controller for a problem that's similar to this. This is a young man whom I took to Boy Scout camp probably about 20 years ago. He's an adult now. But we were out on a course. They call it, I think they call it a ropes course or a cope course. So there's a high wire up here that you can do. I was too chicken. I wasn't going up there. That's why he's wearing this harness. It's a safety harness. And he's waiting his turn. There's somebody else up there in the sky and stuff like that. So he's waiting his turn, and so he's a little bored. And so he decided to pick up a stick, a hiking stick. We're at Boy Scout camp. We all have our hiking sticks. And he decided to stick it on his nose like this. Okay? And you see his hands aren't touching it. So he has to move around to keep it balanced. And so you see the stick right here. So we got a room full of virile young men here. Do I have anybody here who would like to give it a try? Oh, you can squat down. Like this.
Makes it harder.
Right. Okay. So we had a lot of fun watching this. He was a short little kid back then. He's a little taller now. So this is a problem that has some. It's not just fun. It's similar to several other types of problems. It's similar to the problem of sending a rocket up in the sky. Okay, a rocket goes up in the sky because there's thrust at the bottom, but you got to keep it upright. Otherwise, the rocket goes like this. All right. Has anybody maybe visited someplace and seen people going on tour in a city, and they're all riding those Segways? You've seen a Segway? Okay, a Segway is inherently unstable. And so it requires some automatic control to keep it upright. Okay? The riders aren't keeping it upright. They're enjoying the ride from the automatic control. So we're going to take a look at how we design the controller for this problem. Okay? And it's going to be a phase lead type of compensator. All right, we're going to do a simplified model. The model is inherently nonlinear. You can imagine there's sine of the angle involved as gravity works on it, so it's nonlinear. There's the reaction time of the human body. Okay, there's a little bit of delay there. Okay, so for example, if you're drunk, you're going to have a much more difficult time than if you're not drunk. So we're going to ignore some of those issues. We're going to ignore the nonlinearity. We're going to assume that you can instantly move this thing around, and we're going to work with a simplified model. And so the simplified model is this. This is classically called the inverted pendulum problem. And my pen is running out, but that's okay. I think I got another one. And so the plant has a model that looks like this. Okay, so you can imagine this is a mechanical problem. This is a mechanical problem, and we all remember that from Newton's law, force is equal to mass times acceleration. Acceleration is the what derivative of position? Second derivative, right? So we're trying to control, in a sense, we're trying to control position. We're trying to control angular position. And so if you were to write the dynamic equations of this thing and you think Newton's law, okay, force is equal to mass times acceleration. Force is equal to mass times acceleration. Acceleration is the second derivative of position. You would expect probably to see a second order differential equation. And so if we do a transform of the second order differential equation, we end up with a second order model, which is why we have two S's here. Okay, it's second order. And then, so it's second order. Think of this as mechanical system. Acceleration is second order derivative. It's the second derivative of position. Okay, second order Mechanical system is second order, so that's why it's second order. And then you notice here there is a pole in the right half plane. What does a pole in the right half plane tell us about the system? It is unstable, and that's what we expect. Yeah, it's unstable, right? For any initial condition, it's unstable. So this is the simplified model that we're working with for the plant. And so the control system we're going to look at today is this. This is our model. This is the plant. And we're going to design a compensator, C, today. This is our compensator. And we're going to use, this is going to be a phase lead. Okay, a phase lead. And remember, a phase lead if we look at the phase as a function of frequency, remember it does this. And this is positive phase. It could be as much as 90 degrees. In general, it's not. But this is lead. Okay, it's positive as a function of frequency. It means that the output, if you apply the sinusoidal input to the system, to the compensator, the output would look like it's actually ahead. Okay, so if you were to plot it in time and say this was the input, if you plot the input, the output of the compensator will look something like this. Okay, this is the output. What we're saying is the output looks like it's running ahead of the input. Okay? This is like anticipation. Okay? Phase lead is anticipation. Okay? Another word, another synonym for anticipation, another word for leading is predict. Okay? Anticipation, prediction. If you know in advance what's going to happen, you'll probably do better at whatever the task is. Okay? Yeah, if you know in advance what's going to happen, you'll do better. That's what we always wanted to do. That's what people in the stock market want to know. They want to know anticipate what's going to happen so that they can make money. Okay, so this is what we're going to do. We're going to do this design of a phase lead compensator, but we're going to use frequency response techniques. Okay, so what I've handed out is this Bode diagram. This is the Bode diagram of just this function alone. We have just this function alone. Okay. If you wanted to do this on your own time, what you could do is you would say G is a transfer function. The numerator is, let me see, actually I have a little bit of gain here. I put a gain here of 2. There was a gain of 2 in there. Let's change that to a gain of 2. So, and I know that because this has got 6 dB of gain here at low frequency. And then the numerator would be the convolution of S plus 1 and S minus 1. We convolve those. Okay? So that would be this model. And then what I did is I said, give me the Bode plot of G. And I turned on the grid. Okay, you'll get a picture of something somewhat similar to this. Okay? MATLAB will actually probably stop it right about here, because they're saying this is not very interesting. So they'll probably just plot this range. But I asked MATLAB to actually calculate a little bit further, and I went out to a little bit farther range. Okay? All right, so let's look at a potential design specification. Okay? Here's our desired performance. What is our desired performance? Our desired performance is, let's suppose that we have a 0 dB bandwidth, a 0 dB bandwidth, 10 radians per second. Okay. Bandwidth is telling me how quickly this thing responds. Okay, so let's just say for sake of argument, I just choose 10. And I desire a phase margin 60 degrees. Okay. That's our desired performance. So let's study the frequency response and see what we really have. Let's see what the actual bandwidth is. All right. So here's the magnitude plot, and here's the phase plot. We can barely see everything. There we go. Seems a little out of focus. Maybe that'll help a little bit. So what I want is I want a 0 dB bandwidth of 10. So here's 10. So I want this to go through 0 dB at this frequency. 0 dB is up here. I want this to go through 0 dB. I want this to go through 0 dB. So I see there's not enough gain. So that's one issue. And at that point, 0 dB, that will be the gain crossover. I want to look at the margin. If I look at the margin and look at the scale here, what is my margin? What's my margin right now? I have no margin, right? So what I notice right now is currently I have no margin. So I need 60 degrees. Okay. Now the compensator we're going to look at is C of S. We got a gain K. We're going to do it S over omega Z plus 1 over S over omega P plus 1. Okay, we're going to write it like this. I think in my notes I might have just got lazy with omegas. I just said Z and P. Okay. So the phase characteristic of my compensator, this is omega. The phase is going to look like this. And what I want is I want 60 degrees. Okay. And I want to put this is, I'm calling this omega 1. I want to put this, or omega m, which is where the phase is maximum. I'm going to set it equal to the desired gain crossover. The gain crossover, 0 dB bandwidth, this is omega 1. Okay. So basically I'm going to come here, what I want to do is I want to put the phase, I want to put a compensator right here and make the phase come up 60 degrees. Now on this scale, you're not going to see 60 degrees. MATLAB has got said from here to here is only 1 degree. Okay. But basically, conceptually, the idea is that I want to put a pile of dirt right here. Okay, but I want this to be 60 degrees. I want to get a margin. And at the same time, I want this gain to be adjusted so that it goes up through 0 dB. So that's what we're going to achieve. Okay. So let's take a look at the different equations. We want this type of compensator, which means we need a 0 and we need a pole. We need a 0 here, and we need a pole here. And we need to figure out how big the separation is. So let's calculate alpha. Okay. We need 60 degrees from the compensator. So we calculate alpha, which is the ratio of the pole over the 0. How do we calculate that? we use the formula that alpha is equal to 1 plus sine theta m over 1 minus sine theta m. And I'm going to need some calculator work here. Okay, guys? So this is going to be 1 plus sine 60 degrees divided by 1 minus sine 60 degrees. The sine of 60 degrees is square root 3 over 2. Okay. So somebody please calculate that ratio for me. Say that again, 13 point. Okay. If we were doing this on a slide rule, a wooden calculator, we would probably get the number 14. Okay. Call it 14. Okay, that's close enough to 14. Or 13.928. So now I know the ratio. I have one equation now. I have one equation that says 14 is equal to omega p over omega z. Okay, so that's one of my equations. But I have two unknowns, so I need another equation. I need to put this peak, I need to put the peak in the right place. Okay, I'm going to add a bunch of phase lead right here at the desired gain crossover. Okay, it's the desired gain crossover. So I'm basically working on this line right there. I want to put this maximum phase right here. This maximum phase needs to be set equal to omega 1. So basically, I want to put omega m. What is omega m? Omega m is the square root of omega z times omega p. I want to put that at the desired gain crossover, which is equal to 10. So I set these two equal to each other. So I now have another equation. My other equation says that 10 is equal to square root of omega z times omega p. Okay? So I have two equations and two unknowns. Two equations and two unknowns. Let me ask everybody in the first, second, and third row to find omega z. And if you're in the fourth, fifth, and sixth row, to find omega p. Two equations, two unknowns. That's your job. Talk to each other, come to an agreement on what is omega z and omega p. We have two equations, two unknowns. Find omega z, omega p, or z and p. So I'll leave that up there. We'll get some numbers.
Omega p should be
37.41. Anybody else on that row get that? 37.4? Yeah. Sanity check. It needs to be bigger than omega m, and omega m is equal to 10, so that makes sense. How about omega z? Anybody got omega z? 2.67? 2.7, 2.7, 2.7, 2.7. Several people said 2.7-ish. Okay. So we come back here to our Bode diagram. 2.7 is about here. Let's see, 2.7 is about here. And omega p is 37.4, 10, 20, 30, 40, 37 is about here. Okay. And omega m is right here, geometrically in the middle. The distance from here to here and the distance from here to here should be the same if I've done my calculations right. And this ratio should be 14. From this to here, it should be about 14. Okay. All right. So we're going to put this here and put this here. So here's omega z and here's omega p. So what's going to happen now is we're going to put in a compensator, and we're going to put in a compensator. I'm just going to sketch in the compensator somewhere, any old place, right about here. Here's the compensator gain. And this is going to start rising at a gain of 20 dB per decade. So 20 dB is about this much. So in 1 decade, it would go up about 20 dB. I'm just kind of eyeballing it. Something like this. Okay, this is the magnitude of the compensator. This is the phase of the compensator. Okay. So when we put in the zero end pole, put a 0 right here, this is going to start increasing. This slope here is going to be plus 20 dB per decade. The compensator has some increased gain. And then when it hits the pole, the gain quits increasing. Now what we need to do is we need to know how big this is, and we also need to know what this is. So by adjusting k, this whole thing moves up and down. Okay? By adjusting k, the whole thing is going to move up and down. The 0 and the pole give us a little bit of gain also. So we want the total gain of the compensator and this part to be this much gain. Because right now we don't have this going through 0 dB. It's going through at about, minus 34 dB. We need to add some gain. Okay, so we need to compensate for that. Right now, at omega 1 equal to 10 radians per second, the gain is too low. Minus 34 dB. Okay, let's study that. Okay, kind of zoom in there. We want the gain crossover to occur right here. But I'm not quite there yet. I need 34 dB. Okay, I need 34 dB. I'm just eyeballing it. Okay? I need plus 34 dB from the compensator. Okay? I need plus 34 dB from the compensator. And we remember that the compensator's gain looks like this. This is omega. The compensator looks like this. This is omega z, and this is omega p. And right here in the middle, this is omega m, which is where I get the maximum phase lead, I've set that equal to omega 1. I've set that equal to omega 1. And so this is the gain k expressed in dB. And then right here, because I'm halfway between here and here, this gain is k in dB plus 10 log alpha. This is base 10 log. So this is the amount of gain that I can get from my compensator. That's this picture right here. I'm going to put this compensator right here. And I need this gain to make up this. And so what I'm saying is I have now a formula. So I need 34 dB. I need 34 dB from this. I say 34 is equal to k in dB plus 10 log 14. So alpha was the first thing I calculated, so I need to get this right. So now I can calculate the k in dB. It's 34 minus 10 log 14. Any questions about how we are finding k in dB? Okay, the compensator, we've already taken care of the phase. We designed the separation of this so that the phase will be adjusted, but the gain will also be affected. It's a combination of the gain, compensator gain, as well as the separation of the zero and the pole. The separation of the zero pole gives us a little bit of gain, and the compensator has a parameter k that gives us gain, and those two added together need to be the amount of gain that I lack. I lack 34 dB. Okay, somebody got me a k in dB? 22.5. Let's see if somebody else gets that number. Okay, I see some heads nodding. 22.5. Okay, so then what is k? Okay, I need to use this button. I need to use the 10 to the x button, right? I need to do 22.5 divided by 20, and then raise that to the 10 raised to that. Okay, let's review a little bit. This is the amount of gain that I need in dB, 22.5. Where does this number come from? That's our definition of dB. Okay, if it was EMAG, it would be a 10. And this undoes the log, right? Because the dB involves a log. 20 dB is 10, so 22.5 has got to be a number bigger than 10. Okay, what do we get? Somebody? 13.3. Okay. So now our compensator, now we've got these things. We've got the gain k, and earlier we calculated omega z, and we got omega p. So now we can write our compensator. Okay. So this is our compensator in S domain. All right, so let's take a look a moment for the Nyquist plot. This would be an interesting review, okay? If we take a look at the Nyquist plot for this thing, let's first do the Nyquist plot of just the uncompensated. It's going to look something like this. Here's minus 1. The transfer function initially was 2 over s plus 1, s minus 1, like so. Okay. When s is equal to 0, when omega is equal to 0, I get 2 over negative 1. So I start off right here, negative 2. Then as frequency increases, it goes through this point. And then to complete the plot, I go back to negative frequencies. It goes this way. Okay. And so I go right through the point minus 1. I touch the point minus 1. So there is no margin. Or more accurately, I should say 0 phase margin. There is 0 phase margin. Okay. This is the real axis. This is the imaginary axis. With the phase lead, what's going to happen, and I'm going to do now a Nyquist plot of C times G of S. This is just G of S. With the compensator, I'm going to add some phase lead. And so what's going to happen is the overall gain is going to increase. Okay. I'm going to add some gain here. I'm going to add a gain of 13, so it's going to be a lot bigger than this. So it's going to come like this. It's going to start way out here. It's going to be probably about 2 times 13. This is going to be about minus 26. But because there's phase lead, there's anticipation. The response is going to look something like this. And then the negative frequencies are going to look something like this. Okay? And minus 1 is going to be here. So when I do the Nyquist stability, I'm going to get P is equal to 1 because the plant has one pole in the right half plane. And in the clockwise sense, how many times does this go around minus 1 is going to be equal to minus 1. And so Z is going to be equal to 0. And so I have a stable system. I did not wear my watch today. What time do we have? 37. Good. We're not out of time. All right. Do we have any questions about designing on a Bode diagram the phase lead? Everybody good? Okay. Please remember we have a test on Friday. Phase lead will not be on it. Okay. Phase lead is something we start on Monday. But you should be able to design a phase lag. So we did the examples for phase lag last week. Okay. So all materials that we have covered through last Friday could be on the